Okay. So let's restart. Yeah, as I said, I'm a zoologist working in the building across the street, and I'm looking at reproducibility really from an academic viewpoint, and that is that most people don't care about reproducibility. Is here somebody from the University of Basel? One? That's good. Okay, so this, and you as well, of course. Yeah, sorry. Do I care about reproducibility? I just start with saying that I care about reproducibility as a member of the Swiss Reproducibility Network. And there are several people of this network in this room and also giving talks. And just to announce at the very beginning that there will be a Swiss Reproducibility Conference in June in Zurich. And I really like the URL, reproducibility. Great that this was free for us. So we have a network for discussing reproducibility, and we now do this also in Basel. So so maybe I should say how I started with thinking about those issues. I came back from a postdoc in Oslo in 2005. And then everybody there was already using R in ecology and zoology, and here nobody used R. We used SPSS mostly. And then I introduced R to my colleagues and gave some lectures on statistics. And this was, of course, the basic array of tests and what a p-value is, maybe. And then I told the students that the most important number in their life, of course, is p, and that it should be smaller than some value. And this is really, is still the aim of our research. I think I can really tell this as the truth. And then I quickly recognized that something is wrong with the way I teach statistics. And I found some papers that I'm going to cite. And then I found things like this on Vox a bit later. So everything we eat both causes and prevents cancer. And you know all those things that I usually must explain my students. So what is a risk ratio? What is a hazard ratio? I'm not an epidemiologist myself. I'm a zoologist, ecologist. But of course, we all know that wine is either good or bad, depending on the day and how we feel. And this is, of course, bad for science, because then this will lead to newspaper articles like, this is why you shouldn't believe that exciting new medical study. And maybe some of you remember this, this article from The Economist in 2013. So this was really going through some institutes and was widely discussed. So a long article about what is actually running bad in science. And then in 2016, there was a long article in the first part of Nature with a survey that, of course, only reflects the opinion of the ones who surveyed, because this was an online survey, apparently. But so the result of the survey was that most people who responded, of course, said there is something like a reproducibility crisis. We might have a problem. So what is reproducibility? And I'm not sure, of course, and I saw that in some PowerPoints of some of you, there are also definitions that are a bit different from what I took from this paper from Steve Goodman and John Ioannidis and Fanelli from Science Translational Medicine, still an article that I enjoy reading a lot. And we will put the PDFs of the talk on the webpage, and then there's also, at least in my talk, there's a reference list for those who are interested in. So we have methods reproducibility, and that's something that I think what Andreas was talking about, and that's what I've found most people from computer sciences or even statistics think is the main part of reproducibility, and that is that the methods are reproducible in the sense that they are written down so that the study can be repeated using those procedures. I think what the general audience, the public mostly thinks that is worthwhile thinking about is results reproducibility, or in other words, replicability. And that is the question, can we obtain the same results from an independent replication of a study? And then, of course, the next question is, what is the same results? And then Goodman and Ioannidis go further and say that the most important part of reproducibility might be inferential reproducibility. So given our results, whatever that is, maybe just data, can we draw qualitatively similar conclusion the drug works or is helpful or not from an independent replication of a study. So it's also just a newspaper article that I found funny for several reasons. And this was about one of the first replicability papers, replication studies where 270 scientists produced those famous 100 psychology articles published in Science some 15 years ago. And then the headline, but also what they wrote in the paper was that just about 40% came out with the same results as the national reports. And then they applied several measures of reproducibility, but of course, by far, the most important was, is the second result statistically significant or not? And we all probably know that this is a problem. So this is a lovely webpage. Maybe you know this, the dance of the p-values from psychologist slash statistician Geoff Cumming, who called this the dance of the p-values. And he very simply just simulated random samples from, of course, we know this population because it has a true effect of 10 and a standard deviation of 20 and a power of 50. And of course, because we have a power of 50, every second study will turn out non-significant. And then he has a nice animation on the internet making beep for each, whether you have three stars or 2 or 1 or a blob if you have a non-significant result. And this is just what we expect. But the problem is that people, at least people I work with, usually don't know this. So they usually interpret an outcome that has a different effect estimate, a different interval, as though just results that are not the same. And this is the problem because they all come from the same population. And we would expect them to be all significant with a very high power. So then there were a couple of articles appearing like this one in Nature Methods. The fickle p-value generates irreproducible results because of this wide sample-to-sample variability in p-values. And if the power, of course, is low, then we have necessarily a lot of non-significant p-values. Now, in the last couple of years, I was quite lucky in being able to work with Sander Greenland, a statistician, epidemiologist from the US, and he's quite a loud voice in this entire statistics reform movement. And this is from a paper that we wrote, and actually I'm not a statistician, so I learned this from Sander, that we should not blame the p-value because, of course, the p-value is not supposed to be reliable because it just reflects variation in the data from sample to sample. That's also something that Stephen Zen wrote in some papers, a statistician from Basel, as you probably know. So just as effect sizes estimates vary from sample to sample, p-values will necessarily vary as well. But we say this is all how it should be. The problem is only if then people come and have a single study and define based on this single study whether they can say yes or no to some hypothesis and just sell this as a sort of truth. And we say this is overconfidence, and then in the internet on what was Twitter, I found this nice tweet about dichotomization. So we wrote a comment in Nature also that you might have seen because it was actually, I think, quite widely discussed. We had a lot of signatories, and actually we aimed for something like a couple of dozen signatories. But then within 2 weeks, we had 800, and then I really had to stop collecting more and close the list. And in this commentary, we don't say, let's bend the p-value. We say 3 times p-value is fine. But of course, people wanted to read in this article that we were some of the p-value banners that you might also have heard of. But I think we are not. And it's just that the things we say have been said for decades, if not 1 century. Right from the start, people have said things I'm going to tell you in a sec. And we have by far not been the first one. So one of the first papers on the problems with statistical significance was published right before it actually was defined by Ronald Fisher as this famous 5% 0.05 threshold by Boring, psychologist in 1919. And then this is just a collection of more or less randomly of papers that are just brilliant for the title, The Earth is Round, because it's significant. And then there was this famous 2016 statement on p-values by the American Statistical Association. And I was very happy when I saw it. I don't know how you felt about it. I found that it was a bit wishy-washy. And then I also saw a talk by Stephen Zen, who was one of the 20 co-authors, who also says on YouTube, yes, it was wishy-washy. If he would have been the only author, it would have been better. And each of those 20 authors, of course, said the same thing. Because there have been people with completely opposing opinions on this panel who wrote this statement. Yes, and then there have been a few people, and that's mostly editors of a special issue of the American Statistician who made a conference. Has some of you been there? No. In the US, I think in 2018 or 17. And then there was a special issue collecting 40 papers. And we wrote this article I cited before, and I'm going to cite later. And because of this article, we were actually invited by Nature to write this commentary. So, and the main topic of this Nature commentary is really something that annoys me most when I'm sitting in the next building and the seminar room, and in each and every seminar, for sure, the speaker will say, here's an average, and they are the same because they are non-significant. And that's just, it's just a joke, of course. And then, and I also, as an editor of journal or as of journals or as a referee, you often find such sentences. So there was no sex difference. And then in brackets, there was the sex difference. And the sex difference was 100 against 67. And that's a difference. Only it was non-significant. So, and this is something that Fisher wrote papers about, I think in 1935, that absence of evidence is not evidence of absence. And we all know the saying. It's just really hard to act like that when people give a talk. Or also in my early papers, I really made this fallacy. And then we checked, or we did not check ourselves, about 800 papers that have been checked in other papers. And we just collected the numbers and added. It's about something I could have said before already, that in about half of published articles, people just sort of prove the null hypothesis, and that's simply not possible. So it can become serious, and that's an article we actually wanted to cite in our Nature commentary, and the Nature editor said we did not allow this for political reasons. They said that if we blame mothers for taking antidepressants during their pregnancy, then people will talk about this and not about our subject. And I don't know, maybe they have been right. So this is an infamous article that appeared in 2017 about autism spectrum disorder and antidepressants in pregnancy. And you see that they have a barely significant or barely non-significant result, because the confidence interval just barely overlaps the null hypothesis of no effect, hazard ratio of 1. And then they write, so compared with no exposure, not associated with autism spectrum disorder in the child. And that's, of course, depending on your interpretation. So one can use this confidence interval to draw a compatibility graph or p-value function. You probably know this. I mean, it's a curve of all the different null hypotheses tested. Not just the one of 0 effect, of no effect, which would be to the left side. So this is the p-value that they actually had. And then we can see that, of course, the most compatible value is the observed point estimate. A hazard ratio of 1.61 gets a p-value of 1 if we test it, just meaning that this is the most compatible value with the data and the model. No surprise, because that's our point estimate. And what I always find striking is this doubling of hazard. So something really interesting from an epidemiology, don't know, medical point of view. So this doubling of hazard is, of course, highly compatible with the data and the model, because it gets a p-value of 0.37, so much more compatible than actually the null hypothesis of no effect. And this is also what we wrote in our paper. So mostly based, of course, of what Sander explains to me. This is how we would formulate this. Given our statistical model, our estimate was what we observed. And then, of course, we think that one should describe the interval, describe uncertainty by saying that everything from the null hypothesis of no effect until, so the other side of the interval, about 160% hazard increase, was reasonably compatible with our data. And then, of course, the most important part is what they also, in the paper, they say that other studies have found almost the same risk increase. So if anything, their study supports a risk increase and does not disprove that there is a risk increase. But of course, because they wrote this in the abstract, this was cited in the press and on Medscape, antidepressants, no link to autism. And well, I'm agnostic. I'm not a medical researcher or an epidemiologist. This sounds just troublesome to me. So back to this nice, I think it's called a forest plot, is it? I'm not a statistician. I only observe as a researcher, I observe all those studies, how they switch from one study to the next. So that's about antibiotic prophylaxis compared with no treatment in colon surgery. And of course, studies have switched from non-significant to significant to non-significant to insignificant and so forth. And the only thing we really care about, I hope, is this point at the end, which is the sort of meta-analysis. And we all know those problems with meta-analysis because, of course, there are ways to try to correct for publication bias, but it would just be nice to have all those non-significant studies that are on this plot. But the non-significant studies usually are in our file drawers, and this is still one of the pictures I enjoy most when I look at it, because it's 1.3 million results for Medline, the new paper by Van Zwet. And what is missing are the non-significant results. Point. I think one can hardly see this in a better way. And just something that I need to mention also, again, I don't think I have anything against p-values. I'm just not a fan of this dichotomization thing, because it also, as soon as we select results, we get something like effect size inflation, truth inflation, Wiener's curse, all words for the same thing. We could select results because they are yellow or because they are round instead of square or whatever, and then we would get a bias towards yellow or round results, of course. In this case, we select results usually because they are statistically significant. And unless we have a power of 100%, only the largest effects usually become statistically significant. That's just how it is. And if you then look, publish or interpret, look at, publish or interpret only our statistically significant results, then we get a biased impression of the world. And this is now from cancer biology. So 112 replications. And what is not surprising, of course, is that the original findings have been massively on the bias towards significance, and that in the replication, the p-values varied until about 1. And what's more troublesome is that this, of course, also came with an inflated effect size in the earlier studies because of this Wiener's curse, and that the median effect size was just 1/7 of the originals. We usually see things that are too good to be true. If we select results for some reason, and that's a problem that I'm really curious maybe you have the solution to that. Maybe there are filters that we can apply without a bias, without creating bias. I'm just not sure there is such a thing, but that's something I would really like to discuss with you. So I think our conclusion is more or less what this other Nature commentary wrote. So what we wrote as a title in the American Statistician article is more or less what the other article says. Just let's try to remember that single studies are a problem. And now the question, of course, do we have an impact or not? And then we have this picture. Here's on the picture. So this is the clinical trial unit of the university hospital. And they invited me in, I think, was it 19 or 20? Thomas Fabro, yeah, the former chief of the clinical trial unit. And he gives now, luckily for us, he gives the lectures in introductory statistics for biologists at the University of Basel. And so that's me. And I did not print those T-shirts. I think you printed them. And you took just words from this Nature article. I found this funny. And then we had, so this was the clinical trial day with about 300 or 400 people sitting in this room, in another room, of course, and they all nodded. So I did, even the dean of the medical faculty nodded his head. And so they are, I don't know, many people understand what we are saying, what many people say since decades, but people just don't act like this. And this is the, oh, not the, do I have time? So it's, yes, I still have a bit of time. I'm an ecologist, evolutionary biologist. The question is, do we have an impact? And I'm afraid not, at least not in my field. So this is about 50 papers from one of our best journals. And it's fine to have many significance tests in a paper. But if you have, I learned, if you say something, we reject this hypothesis, or we make a conclusion about a hypothesis, then you should have two hypotheses and not just one. And you should also have ideally some pre-study power calculation, and that's simply not done in my field. And my conclusion is that zoologists, ecologists don't test hypotheses. They just use those p-values as descriptive agents to describe what they found, and then write a paper about, I confirmed my hypothesis. And that's just ethically a problem, I think. Only people don't see it that way. I hope in your field it's better. At least I heard that, all the things that we can discuss later. And that's something that I really laughed from one of the papers of this journal. I think I've never seen a worse table. So these are 102 significance tests. And the scientific content is exactly zero, I think. So there's really nothing that you can continue working with later. So, and then we also wrote preprints together with Andrew Gilman, and the last, because the one person who loudest argued against our Nature commentary was John Ioannidis for some reason. And there's also on the Andrew Gilman blog, there's something like, I don't know how many pages, so probably one of the longest blog posts which people were arguing. I actually did not read through it yet. Maybe when I'm retired. So we responded to John Ioannidis, and these are classical Andrew Gilman sentences. And that's my conclusion for my talk. I'm not so sure we have a replicability crisis or a reproducibility crisis. I think we have mostly a communication crisis. And maybe you can try to discuss this or work on that in the future. And again, this is the last post. I also have, of course, a web page at the university where you can find those papers, or then later on the homepage of the society. So thank you. I think we have something like, oh, I was way too fast. Sorry, what? I can say more. About what? Okay. I do nightingale research mostly. I can tell you why nightingales sing at dawn or at dusk, or why they actually sing at night. And at this point, I usually, now very early when I give such talks, I usually tell people that I never in my life did a replication study. I never did a meta-analysis. And then there's usually a rumor because people understand that I'm not an expert and that in my field, we simply don't do those things. So I'm sorry. I think we are really behaving very bad. And my only excuse is that, so no zoologists in this room, that it's simply, it's not life-threatening if something is not replicable. And I know it's recorded. I think that was a problem about recording. If people tend to be honest, then they might get a problem if it's recorded later. So I think in most fields that I see, it's only about papers. People are not interested. At least if it's not life-threatening, that something is not replicable, people are not interested in the question of whether it's replicable or not. And I'm not sure they use statistics to define that. I think they just repeat the experiments. And this is, of course, how it should be. Let's just repeat our experiments and see whether the outcome is the same, whatever that means. So we will discuss this, of course, later. Also, maybe somebody has a question already? Yes.
It's a bit complex to start to talk about like p-value and all of that. Sometimes you want to have one article that is one method, what we define. And I find it extremely difficult then to weigh all the decisions that have been taken, all the what if, and so I wonder if you have any that like how we can communicate better but still make great science.
Yeah, so the question, I think we should work with a microphone later. So the question is how to communicate uncertainty, actually. And the problem that we have is that we usually need to break down our messages to some sentences for various reasons, because we want to convince people, because we want to tell a story, because we need funding, because the newspapers like headlines. And so we must break, usually I would say, why do we need to break down? So what is the outcome of academic research should just be data that are reliable. And then maybe somebody goes and collect those different studies, publishing data, and then makes a meta-analysis. This is how I think science should work. And I don't know who invented so for example, if you, Darwin, he's quite, used to be famous, and he took like 25 years for writing a book. So he did not publish in our sense. And I'm not sure he has one, well, the headline would be, it works without God, or I don't know. There are strong headlines that you could imagine on Darwin's work, but I mean, he just collected so much evidence without any statistics, but just by observing and by thinking. And then at the end, in the middle of his life, he published one book, and at the end of his life, he published one book, and this really changed science for the next 150 years. I don't know who invented the system that we have now, but I think it's really not, maybe it's not good. And I'm not sure this communication is really necessary for science. But this is, of course, I mean, I don't have a solution because the system is how it is. So we need to publish. Some people want to be in the newspaper. Sorry. Do you want to? Because if you don't take the microphone for the people on Zoom, I need to restate all that you say.
So Valentin, you said that it maybe happens in your field because there are no lives at stake, but now in clinical research there are. And I know, yes, we have like clinicaltrials.gov where we register what we intend to do, and then often it is basically not what we're doing in the end. And we have the problem of publication bias, negative results not getting published. So you're not getting out of this conundrum as easy as saying, yeah, you know, there's nothing at stake here. But there it is, and there we also have a problem, whether it is reproducibility problem or a communication problem, I don't care, but it is a problem.
Yes, but you have pre-registration, and I think some of you also use power analysis before you do something. If you use statistical significance, you should use power analysis, no? I don't know. That's my feeling, because I don't know. So I think you make some things better.
We had a team, someone in my team presented this Wednesday about this specific problem of power analysis, you know. So we have an interested party. They have 10 explanatory variables. They want to find out whether something causes a heat stroke or not. And they say, yeah, they believe 30 is enough. And then we did a power analysis, and we ended up with 2,500 based on what the fact says they want to show. No, so
Yeah.
and it's just discussing, and we'll see. Maybe we end up with 30.
Yeah. I think you probably all know those papers that average power in neurobiology is like 20% or something. And so that's just, we are playing a game. It's not science, and it's just fishing, doing cheap. I mean, that's also what Andrew Gilman and others are saying since decades. So this is really doing cheap studies and then fishing the ones that are significant. That's the only way you can publish your papers with 20% power. And of course, this leads to hugely inflated effect sizes. And I hope there are fields in which this is not the case. Sorry. Yeah.
Thank you for the talk. It's really nice. I really like that you kind of separated as well the reproducibility and communication. One comment on the communication, for me, it feels like a prisoner's dilemma, right? And I think like if someone else sells it better, you kind of need to sell it better to be heard, right? But I have a question on the methodology part about the reproducibility part. I struggled, like in my PhD, to reproduce methods of other papers because it was just not detailed enough. How do you think we can solve or make kind of people be more detailed on the methods, at least to have like one part of the reproducibility kind of solved, which is doable, right? We just need to be more detailed in writing down, but people don't do it. I don't know if it's because it's boring, it's tedious, or the word limit. Yeah. Yeah. Or yeah.
Can you repeat just so that what she said? Because
okay. One issue is the word limit on journals. So you need to kind of trim down the methods. And yeah.
Yeah, absolutely. And what I usually observe is that people tend to describe what turned out to be like they expected and what is positive. And then if I tell my students, yeah, look, you should also at least in your PhD or at least in your master, you should also write down what all the failures. That's because usually you have like 10 failures and then one significant result. And then of course this is impossible. It's because students know that this is not science if you write down the failures. And they are, of course, we know that failures are at least as interesting as the things that turned out well, but we don't have a culture for that. I think there has been a journal of non-significant results, but then I think it disappeared because people did not submit. And well, okay. Yeah.
I would like to comment on this aspect of methods description when it comes to journal articles. I think I have a somewhat different opinion because when we now publish our papers, we sometimes even provide the entire code, even for medical journals as zip files. It's not an issue at all with all the online material available. First, the more problematic part I've experienced as being an editor for some of even the clinical journals, and typically the methodology editor, is that some of the journals require people to submit the original study protocols and the original statistical analysis plans. And one of the funny ones I had on my desk about 2 months ago was, if we assume an effect size of XX and the power of XX, then we require the sample size of XX. This was the original study protocol. It was the methods description for the paper, and this was submitted to the journal. And you can probably imagine what my recommendation to the editor-in-chief was for that article. So in my opinion, it's more the content and the understanding, the methodology understanding, rather than the publication process about the methods. It is what we accept as reviewers, as editors, what should be described in the methods, how detailed.
Just one comment about the limitation of a journal on your method description. I would assume that you wrote up the description of your methods independent of the journal, and that could be put online without the blessing of the journal if you really care about this, or it's an excuse to me. But that's not my question. I'm just really curious, Valentin, how did you learn statistics? Was it a statistician that trained you, or were you self-taught? And did you learn this from textbooks? I mean, how did you learn statistics?
Yeah, thanks. Very straightforward question. Yeah. So I learned statistics from textbooks. Yeah. And I'm not sure whether I know statistics. So for example, I really stopped doing the analysis myself because I hired a statistician, and that's good, but it's also partly bad because it's really, I mean, my students need to work with R, and she's also a Bayesian statistician, and that's way beyond the capability of most people at our institute. And so I don't say that I simply trust what she does, but I mean, I'm confident, I completely trust what she does, but we discussed this. And of course, but this is, I mean, you know, all those discussions that people also don't go to a medical doctor or whatever who just does this by hobby. So people usually need to learn things that they do. Yeah. And I'm really, mostly personally, I'm just interested in the philosophical, what people call philosophical. I think it's extremely practical because I think it's really making inferences from our data is what science is about. And so we mostly use statistics for this. Also, there might also be other ways. And I think that's what everybody needs to think about. And the simple question, you know, probably all those, also on the internet, you can find movies on people are answering the question what the p-value is. And it's very funny. And it's really tricky what the p-value is, I'm afraid. And yeah. I think we need so I usually tell my students that this is forget all about zoology and how the different birds are called, because what you need to learn mostly is to know what the p-value is if you're using them. I think that's so straightforward because you're going to interpret this. And that's what I try to learn. Yeah. So now we are almost at the end of my slot. And I just switch this off, and then we have